Good morning, class. Okay, so next up is just a real quick look at curve sketching and how we use the techniques of calculus to continue to develop ideas about functions and curves and sort of building on advanced functions work and some terminology that you guys were introduced to there, and applying it to with respect to taking derivatives with respect to curve sketching and what it means um, to draw and understand and sketch functions. Okay, so just a warm-up and intro, just about really constructing, interpreting graphical models, looking for patterns. This is used extensively in outside of the classroom. Best examples maybe stock market predictions and patterns and analysis of situations, economic and business situations that business analysts might use. A little bit of calculus, right? Absolutely. As some of you will see next year, a lot of business applications in a lot of calculus applications in business and economics. So this is the focus of this chapter: drawing graphs from functions using methods of calculus and introducing first and second derivatives of functions, so we can analyze graphical models and extend some of this knowledge. Okay, so some learning goals and success criteria in this particular chapter. Okay, we're learning properties of graphs and polynomial and rational functions, key features of a given graph, determine intercepts and positions of asymptotes of graphs, determine the values of a function near its asymptotes, and determine key features of the graph from a function, sketching by hand, using Desmos as well, and then determining equations from simple combinations of some functions. Okay, so the learning successful goals would be how to describe and explain the properties of polynomial, rational, and more advanced functions, sketching the graph of a polynomial, rational, and more advanced functions using calculus techniques, so curve sketching techniques. I use Desmos or other graphing technology to graph these functions, and state and understand key features of polynomial and rational functions or more advanced functions. Okay, so a couple of concepts right off the bat here. Okay, increasing and decreasing functions. Now, first up, I'm going to follow the textbook pretty closely and talk about some definitions first, do a couple of examples, and I'm going to pause throughout the video so that you guys can do the derivatives rather than just watch me on the video, and then you can just start up. You can pause your own video and do the work, and then start it again and see what you've done with this. And you might have to do that back and forth in order to move forward with me, but I'm going to, like I said, have you guys build in some time to do that as well. Okay, so quite simply, a function is increasing. We obviously read our functions from left to right, okay? So always from a sort of a left to right feel. Okay, so look here at the left and read it across as we sweep across the function. So clearly this is an increasing function, this first one here. It's increasing because as I move along the x-axis from left to right, my function is moving upward in an upward direction. This next one is a decreasing function. The definition is that the next value of x, so the function at x subscript 2, okay, is always less than the previous value at x subscript 1. So x1, function at x1 is greater than the function at x2 over an interval, okay, a to b. And then the other terminology obviously is it's constant when it's a flat horizontal line. So these, okay, this is the idea here. Now, before we get into this, I'll just give you a glimpse ahead here. Look at the slopes of these functions. Okay, so this slope would be positive and it'd be increasing. The slope of the tangent line would be negative and it would be decreasing, and this slope would be a flat horizontal line. So that's going to be the first derivative test here as we get doing some of these questions. Okay, really quickly, and again, this is all explained. The answers are explained, text-based answers are explained in the lesson. This video just supplements the lesson. Okay, so quite simply and easily here. So we've got, okay, sort of a continuous, somewhat continuous interval. Okay, so we've got, let's define our domain. Okay, so for all values less than or equal to 7, okay, and that's set notation. As interval notation, I'm going to include 7. Okay, so it's 7 and everything downward. Okay, so where is it increasing is the first question. Okay, so it's increasing, okay, on when I look at left to right as the function goes up. So if I follow from left to right, here's my first decreasing section. Looks like it's increasing here. So I'm going to write increasing on the interval between -4, and -2. Okay, don't confuse this as an ordered pair. It's an x as an element of. Okay, in set notation, that would be, okay, so x is continuous, and it's between -4 and -2, and I just close my bracket. Now, I'm not going to use equal signs on this, okay, unless, okay, I know because at the point, it's actually changing here. Now, there's another increasing function area, so there's another increasing area, okay, as x is an element of all the way over here to 4 and all the way up to 7. But I can close off my square bracket here because 7 is included in this and in set notation. Okay, so from 4, x is greater than 4, and x is less than or equal to 7. Now, set and interval notation, you guys can use whatever form you want. They both explain, there's a good explanation and some good examples in the notes on the online class. Okay, what about a decreasing situation here? I'm going to stop this, okay, temporarily, and you guys can pause this, and I'll fill it in, and you can see if you can complete, okay, the rest here. Okay, so I'm going to pick this back up, and I've stated the decreasing areas, okay, so just on the graph. Okay, that's when, as I read it from left to right, when it's going down. So the first one is from infinity to -4. The next one is from -2 to 0, and those are the only two decreasing intervals, both in, okay, interval notation and set notation. You don't have to write the x as an element of that interval, and then if you write it in interval notation, the constant area, okay, where the graph is flat, goes from 0 to 4. Okay, that's expressed there, and then there's some extreme points. I didn't ask you necessarily to state these, okay, but I did include them here. So my extreme points are at -4, right? That's a minimum. That would be a local. Oh, that looks like to me it's a global or a local minimum. There's another extreme, a local max at -2. There's another extreme at 0. That's another local or global minimum. And then again at 4. Those are changes. I know that's a constant line between 0 and 4. Okay, so all the points along there would be global minimums. But the point I identified, the extreme points of x equals 0 and x equals 4, that's change points. Okay, so those are key extreme points, because in the first one at x equals 0, it's changing from, okay, it's changing from decreasing to flat, and then it's going from flat or constant to increasing here. Okay, let's move along here. We're good with that. I'll just scroll down again so you guys can see exactly what it is we have to state and move forward with, okay, a couple more examples. Okay, so let's find the increasing and decreasing intervals, okay, of this particular function here. Now, you guys in your notes, I noticed in the photocopy notes, okay, it should be written a little differently. It's a function x over top of x squared plus 1. Okay, so I need to take, the first thing I need to do is take the first derivative of it. Okay, that's how we're going to do this test, and we're going to look at areas where it's increasing and decreasing. Okay, so the first derivative involves a quotient rule, and I'm going to, okay, pause and let you guys do that and see if we can pick it up here in a minute. Okay, so I use the quotient rule to find the first derivative. Now the steps are here and shown. Okay, it left me with an expression -x squared plus 1 all over x squared plus 1 quantity squared. Okay, so the intervals of increase are found by setting the first derivative equal to 0. All right, sound familiar, right? These are changes to the graph. I'm going to call these turning points. And these are situations when the derivative equals 0. These are situations where the derivative has either been increasing, and then at that point it changes to decreasing, or the opposite. It's been decreasing, and then at that particular point where the derivative is equal to 0, it all of a sudden becomes increasing. So they're turning points. The function makes a significant change in the direction that it's going here, and the change looks, okay, via increasing to decreasing or decreasing to increasing. Okay, so I set the first derivative equal to 0. Okay, that just means the numerator is equal to 0. Okay, that's over here, this expression. So I found some turning points on my function to the plus and minus 1. Now I'm going to see which is which. Okay, where is it decreasing and increasing? I'm going to use a sign chart, a modified sign chart, to do that, and I'm going to do it at those, okay, at those particular points. So once again, I'm going to pause and let you guys set up a sign chart, see if you can, okay, work on this. Okay, so I set up my sine chart broken into intervals at the points that I found for my first derivative here. Okay, so that was between, so again from left to right, so I'm looking at an interval from negative infinity to negative 1. Okay, then there's a break there because that's the turning point, right? That's the turning point. Okay. And then I go from negative 1 to 1, and there's a break. There's another turning point here. And then I pick it up from 1 to negative, or sorry, from 1 to positive infinity. And I'm going to check the key points that are in this interval. So I've chosen just arbitrarily x equals negative 2, it happens to be in this interval. X equals 0, it happens to be in this interval. And x equals 2, it happens to be in my third interval. So now I'm going to take the derivative function. Okay, that derivative function is negative x squared plus 1 all over x squared plus 1 quantity squared. And I'm going to figure out the sign in each of those things. Okay, so let's put in negative 2. If I put negative 2 into my top of my function, that's negative x squared. So negative 2 squared is positive 4. I take the negative of that right up here, and then I add 1. So regardless, that's going to be a negative interval. Okay, the denominator is x squared plus 1. Okay, no matter what I put in there, if I square it and then add 1 to it, and then I square it again, that's always going to be positive. For the derivative function, okay, this derivative function right here, okay, the denominator is always going to be positive. Okay, so I have a negative divided by a positive, that's 0, and what that means is if the slope is less than 0, it's decreasing in this interval. Okay, let's go over to 0. Let's put in 0 here. So let's put 0 into this function up here. Okay, 0 squared is negative, is still 0. 1 plus 1, it'll be a positive over another positive. So a positive over a positive of my derivative function is always going to be positive, and that means it's increasing. Okay, if the derivative of the function is greater than 0, it's increasing. Okay, and then my turning point, okay, is at 1, and then I have to check for 2 here. So let's put 2 in here. 2 squared is 4. Negative 4 plus 1 is a negative. And then as we know, the denominator is always positive. So we're back to the decreasing function. And that's really all we have to do. We should just state, okay, this statement here, okay, so it's increasing on, okay, oh, that's decreasing, and it's increasing on, okay, sorry, that first one is decreasing, okay, and that's represented by, okay, next question. Okay, a little more complicated function. Again, make sure you have this in your notes that it's x minus 2 multiplied by the third root of x squared. Again, I'm going to let you guys take that. This is going to be a product rule, right? I see a product right in here. Okay, so it's going to be a product rule. Or I could, if I wanted to, I could expand. Actually, I could expand this in, okay, and just use the power rule on it if I wanted to. But either way, I'm going to pick up the video again after I've taken the derivative and started to solve for x and see what sort of situation we've got here. Okay, so take a pause and get cracking on this derivative. Okay, here's my derivative. Okay, I use the quotient, or use the product rule. Over here, I decided not to expand it. Use the product rule and worked on my derivative. Then I did a quick expansion in this area here. I did a quick expansion in that area in here. I got 2 terms, and then one of them happened to be had a common term x to the 2/3, and I combined those. So that was 1. Coefficient was 1 here, or 3 over 3. So 3 over 3 plus 2 over 3 is 5 over 3. Okay, and that's the proper derivative here. Okay, so next up is what's always next up. That means I have to solve for x in this expression, which really isn't a big deal. Okay, I'll show you a nice little strategy here. I'm going to move my negative term over here. Not only am I going to move my negative term over here, I'm going to write my positive positive exponent here. Okay, so I did two things here. I moved the whole term with the negative sign over, so it became positive 4 over 3, and then x to the negative 1/3 is actually x to the 1/3 when I move it down to the denominator. Now I cross multiply. Okay, so that'll be 5 times 3 is 15. Okay, let me write these terms out. When I cross multiply, okay, that'll be 4 times 3. Okay, so my 3's can cancel. Okay, that's a 3 here, folks. Okay, that's 15x equals 12. Right? Or I've got, okay, x equals 4 over 5 according to my notes. Okay, now when you use this strategy, the cross multiply strategy, we have to identify, okay, right here, okay, a key point here, and I'm going to call that a key point. I want to make sure that we understand that restriction. Okay, so there's a restriction at x equals 0, and that's a point we have to look at in our sign chart as well, because something funny might happen at that change point, right? It's an asymptote, you guys. Okay, it can't be, okay, it can't be 0. Okay, so we have to look at that particular situation. So I've got some intervals here. X is less than 0 when I go from left to right. Then I pick it up at, okay, 4/5. Okay, I'm using set notation here this time. Okay, not interval notation. Okay, and then I, okay, pick up again at 4/5. Okay, so look at the region here, the intervals. It covers everything from left to right. So I go from negative infinity all the way up to 0. 0 is a breakpoint, or a checkpoint is a better way to say it. It's a checkpoint. It was a restriction, but I'm just going to check it. Okay, and then I stop, and then I pick it up again from 0 to 4/5. 4/5 is an extreme point, and then I stop at 4/5 and I pick it up again for 4/5 and beyond. Those are my only intervals here. And again, I'm going to check my, okay, first derivative here. Okay, and I'll use this function to check my first derivative here. And this is going to be a little bit tricky, okay? A little bit tricky to check that. Okay, but I think we'll be able to do that just fine. Okay. All right. I need some points here. Let's go -1. That happens to be an interval. I could go 4/5. I could go 1/2. And I could go x equals 1 here. All right, this will be a little bit tricky. So the sign of, okay, the sign of my first derivative, okay, when x is -1 here. So if I put -1 in here, the third root of -1 is -1, but squared is positive, so it'll be 5/3, okay, and then third root of -1, okay, third root of -1, okay, is -1, and then raised to the, okay, 1 power, still -1 power, and then a plus, okay, so multiplied by -4/3. If this is -1, and multiplied by -4/3 would be a plus, okay, 4/3. So I've got 5/3 plus 4/3 is going to be positive. Okay? And that means it's increasing. At x equals 1/2, a little bit more challenging. You can use your calculator for that. You can put in positive 1/2 in here, positive 1/2 in here, raise those values. We get a situation where it's negative. That's decreasing. At any time you can graph the original function on Desmos, and just confirm that those are in fact happening here. Okay, and x equals 1. Again, x equals 1. We're going to have 5/3 take away 4/3, and that's still a positive. That would be a positive situation. And that's increasing. Okay, so those are our intervals. The intervals. Okay. Okay, so it's increasing between so less than 0 and greater than Oh no. Next one is 4/5. Okay. And it's decreasing. Just using set notation for a change. And it was that middle one that's increasing, so between 0 and 4/5. Okay, I'm going to look ahead at the next one. I'm also going to open Desmos, and I'll do that in a second when I return. Okay, here's my Desmos function, and that's pretty evident that it does support what I found algebraically with finding the derivative and finding those increasing intervals. We had an increasing interval from negative infinity to 0, then decreasing from 0 to 4/5, that's 0.8 down here, and then increasing again from 4/5 or 0.8 all the way for the rest of this interval. So there's the function, and I just got a value of 4/5 of my function. Okay, good. Let's move on to the last question in 4.1, and that's to graph a function, this one here. Okay, so this is from the textbook number 6 on page 170. This is it's going to be a homework question as well too. You're going to be given some information, and you have to just come up with a sketch. It's important that it's a sketch. We just have sketches. We don't account for vertical shifts. Okay, so adding a vertical shift of, let's say, like +5 to a function doesn't really change the basic shape of the function and doesn't have any effect on a derivative, but we just want sketches here. Okay, so here's what we're given in a sketch. Okay, it's differentiable, so it's continuous. That's what that means. It's continuous on the interval from -2 to 1, 2, 3, 4, 5. So I only have to graph my function in between these chunks here. Okay, so the first piece of information that has to be satisfied here is the graph passes through the points -1 and 0. Okay, so -1 and 0, and then 2 and 5. 2, 3, 4, 5. Okay, so those are 2 points. Okay, that's good. The function is decreasing from -2 to -1. Okay, so from -2 to -1. From -2 to -1, it's decreasing. Okay, and it has to hit this point. Then it's increasing from -1 to 2. Okay, so it's increasing. I have to bend and go to -2. Okay, and then it's decreasing again from -2, or sorry, from +2 to 5 in the interval from 2 to 5. Okay, so it's okay. And arrows on the end of it? No, not really, probably not. I'm only defining it in the -2 to 5 interval. Okay, and this could, the problem and the key point here about sketching is this could be a very different sketch. Okay, I could have a very different sketch. Let's do it in red. Okay, that maybe look like this. Oh, without that. Okay, so that satisfies my criteria, right? It has 2 points, and it's decreasing, increasing, and decreasing. I could also have, if I really wanted to do it in green, okay, I could have up here, okay, I could also have, okay, way up here, pretty limited to here because it's increasing the interval. I couldn't go up and then back down. It has to be completely increasing the interval from -1, okay, to 2, okay, and then I could drop like that. So the basic idea is represented with the criteria, the conditions that need to be satisfied here. The sketch is important because it could have other endpoints here, and that's the idea. Okay, I think you can probably do some of these homework questions, get started on it, and I'll post some of these solutions in the homework page on the online class. Okay, good luck everybody, and welcome to Chapter 4.